I used to think, everybody should do everything, but then I realized that, you're human and you have other stuff to do. Amazing. All right, next problem. Prove that square root of 5 is irrational by contradiction. So by contradiction means we start with the negation of the conclusion. So the opposite of square root of 5 is irrational is that square root of 5 is rational. And if your question is, can I write my proof like that? The answer is yes. Whatever abbreviations I use, you're allowed to use on your test. The definition of rational tells me that I can write square root of 5 as p over q, where p and q are integers and they're relatively prime. And what does relatively prime mean? They have no common factors. So now, at this point, we know that what we would really like to do is show that p and q have common factors, because it's the only thing that I could get the opposite of in this proof. So that's what I'm going to try to do. So I'm going to square both sides and cross multiply to get 5q equals p. That's from math. You're not allowed to write that on proof stuff for logic, but you're allowed to write it for this. It's just regular math, yes? Yes, thank you so much. Okay, so now this means that 5 divides p squared, right? Because the definition of divisibility is that if I can write something as having a factored out times an integer, then it's divisible by that. So this means 5 divides p squared. That's from the definition of divisibility. And we've done this proof in class. I think that I have possibly, I don't have a question. So we'll have to prove this to the side. We'll do it later. So we're going to prove that to the side. So if 5 divides p squared, 5 has to divide p. What kind of numbers make this implication true? So besides 5, what kind of numbers could I put in there? So if something divides a square, how does it divide the root of the square? Always. Like, what numbers can I always put in there? No, not all positive integers work. How about 4? If 4 divides p squared, does 4 divide p? 4 does not necessarily divide p. Let's say p is 2. 4 divides p squared, right? But 4 does not divide 2. 4 is a perfect square. So you obviously can't put squared numbers in there. What other kinds of numbers could you put in there? Prime numbers. Prime numbers will always work. So if someone says, prove that the square root of 16 is irrational, you should say, no. It will not work. This is where it breaks. Okay? The entire proof, you could do it with robot brain, but this lemma will not work if you're taking the square root of something that is a square. Okay, I'm glad you don't look shocked. Lemma means a little thing I'm going to go prove on the side later. That's what lemma means, little proof. This is our big proof. Lemma is our little proof. It's not my creation. That is a math word. So if you ever see a lemma in a book, you're like, what the heck is a lemma? I always thought that when I was, an undergrad. It's like, what's a lemma? What's a theorem? What's a conjecture? Conjecture is something we haven't proved yet. A theorem is the thing we have proved, and a lemma is a little thing I proved because I was trying to prove something bigger. Okay, so now I can use modus ponens with 4 and 5 to get the 5 divides p. If 5 divides p, then p is equal to 5 times some integer. And that's a definition of divisibility. Now I'm going to plug this back in to my equation on line 3 and get that 5q squared equals 25k squared. So I have to square p to get that. So that was substitution with line 7 and 3. So now I get q squared equals 5 times k squared just by dividing out a 5. But now I have an equation that looks a heck of a lot like equation 3, so therefore I can also, just from this, can figure out that 5 divides q, right? Because the same lemma that works for p will work for q because p and q are just variables. Well, I forgot to write 5 divides q squared. So I'm going to combine line and 10 together with mode exponents at 5 divides q, but now I have that 5 divides p and 5 divides q by conjunction, and that's a contradiction because p and q were not supposed to have common factors. Okay, I'm not going to do it, but I'm going to show you the structure of the lemma. Doesn't matter if you use q or p. No, once you do it with one variable, it works for all the variables. So the question was, do I have to do it separately for p and q? No. If I prove it for one, it works for all variables. Okay, so you know that 5 divides q in the first row, and it doesn't in all the rest of them, right? Because a sum is divisible by a number if all the terms in the sum are divisible, but the last one's not. So if every term in the sum, except for one, is divisible by 5, then the sum is not divisible by 5. So all of these are not divisible by 5 by definition, right? I was actually separating the numbers by what their remainder is if I divide by 5. So 5k is all the numbers that are divisible by 5, and all the other ones are all the numbers that are not divisible by 5. So then what I do in order to figure out 5 divides q squared is I actually have to put q squared on here. And I actually have to use q to figure out what it is. So the first one is 25k squared. The rest of them, you multiply out this number times itself and show that all the terms are divisible by 5 except for the last one. So I'm not going to finish that because we have 5 minutes left. That's an easy one.